morning, students. Myself, Vijay Shankar, EC Department, Shubhrul Engineering College. Today, we are going to discuss about the filter characteristics of the linear system. We already discussed about some of the linear systems. Now, we go for the discussion about the filter characteristics of the linear system. Filters. There is a different types of filters. We have low pass filter, high pass filter, band pass filter, and band reject filter. What are the four filters? Low pass filter, high pass filter, band pass filter, and band reject filter. See, a filter is a one which rejects unwanted frequencies from the input signal and allow the desired frequency. So filter is nothing but which rejects unwanted frequencies from the input. Think about it is from the input signal and allow the desired frequencies That is nothing but a filter. The range of frequencies of a signal. So what is that here? The range of frequencies of a signal that are passed through the filter is called pass band. So the range of frequencies of a signal that are passed through the filter is called pass band. And these frequencies that are blocked, the frequencies that are blocked is called stop band. Means there is a two bands are there in each filter, either in the low pass filter, high pass filter, band pass filter, and band reject filter. In that, there is a pass band is here and the stop band also. Pass band is nothing but the range of frequencies of the signal that are passed through the filter is called pass band, and the frequencies that are blocked is called stop band. Okay, so first of all, you can see that the different types of filters. The first filter is a ideal low pass filter. An ideal low pass filter transmits all of the signals below certain frequency B hertz. B hertz means here B minus B and plus B without any distortion. The range of frequencies from 0 hertz to B hertz is called pass band of the low pass filter. See here up to the 0 to B hertz, we can call it as a pass band of the low pass filter. It rejects all the signals which lie outside the pass band filter. See, these are outside the pass band, nothing but the stop band. It rejects all the signals which lie outside the pass band. The frequency pH is called cutoff frequency. At this, there is a cutoff frequency. pH is called cutoff frequency of the ideal low pass filter. Since the filter is ideal and the distortionless, the phase changes should follow equation, that is H of F is equal to K into e power minus j 2 pi F into T naught is from the minus B to the B as into the frequency, and 0 for greater than the P. I am taking the magnitude minus 1. So magnitude means and this is a stop band, and here also the stop band is equal to 0. The magnitude is greater than the B. So it does not allow the frequencies outside the pass band. This equation is obtained from the equation 4.53. We earlier derived that it is a distortionless transmission. We already derived the distortionless transmission, my students. Here the amplitude is a K. Can be assumed to be unity. This equation is obtained from the equation the 4.53, means we already derived the expression for the distortionless transmission, my dear students. So that is a H of F is equal to some K is a amplitude, either it is increasing or decreasing, and this e power minus j 2 pi f into t naught as x of t minus t naught is a function after applying the Fourier transformation. That Fourier transformation is x of f. So y of f by the x of f is nothing but h of f. When the k is equal to 1 in this equation, h of f is equal to e power minus j 2 pi f into t naught in the range of minus b to the b, and 0 for magnitude is greater than the b. It does not allow the high frequency values. What is the characteristics of the low pass filter? It does not allow the high frequency values. It allows only the low frequency values. Okay. We know that the transfer function h of f is a Fourier transform of impulse response h of t. Impulse response of h of t. Impulse response, nothing but h of t. Impulse signal is nothing but a delta of t. Forget about that one. After applying here the Fourier transform, not the Fourier transformation, this passes through the system, linear time invariant system. We get h of t. Nothing but it is a response. Output is a response. So for the impulse signal, we'll get in the impulse response h of t. H of t, the Fourier transformation is a h of f. Okay, my dear students. So we know the transfer function h of f is a Fourier transform of impulse response h of t. Therefore, h of t can be obtained for ideal low pass filter by taking inverse Fourier transformation of the function. See why you are getting it is an inverse Fourier transformation. H of f is a frequency. Converting the frequency into the time domain function. For that, you have to apply inverse Fourier transformation. Therefore, by the definition of inverse Fourier transformation, here, see these are the characteristics what we have already. The h of f is equal to the magnitude of k, and it is a stop band. And the theta f is a angle. What is an angle? 2 pi f into t naught. When t naught is equal to 0, this is a frequency here, the f is equal to 0, it passes through a straight line, passes through the origin. This is a phase, the low pass filter phase response and the low pass filter magnitude responses. Okay. We got the definition of the inverse Fourier transformation. You see. H of t is equal to, so h of t integral minus b to b. Why I am taking the minus b to b? In this range only, the value is 1. The a is nothing but here I am taking that is a k. K is nothing but it is a 1 here. So e power minus j 2 pi f into t naught and multiplying with e power j 2 pi f into t. The inverse Fourier transformation of the frequency. What is the formula? Actually, the x of omega is equal to integral minus infinity to infinite x of t e power minus j omega t dt is the definition of the Fourier transformation. Fourier transformation definition. What is the inverse Fourier transformation? X of t is equal to 1 by 2 pi integral minus infinite to infinite x of omega into, here the negative exponential we used, now we can go for the positive exponential e power j omega t, and is with respect to the d omega. Now you convert into the normal frequency values, h of f is equal to x of f in the frequency, my students, Fourier transformation. X of f is equal to minus infinite to infinite x of t into e power minus j, the omega is nothing but the 2 pi f into t dt, and inverse Fourier transformation is x of t is equal to 1 by 2 pi here, 1 by 2 pi, substituting the omega is equal to 2 pi f minus 2 pi f here. You see, when the x of 2 pi f, the shortcut notation is x of f e power plus j omega. Omega is nothing but 2 pi f into t, and d omega means omega is equal to 2 pi f d omega is equal to 2 pi into df, my dear students. Okay, substituting the d omega as a 2 pi into df. If the 2 pi get cancelled, the inverse Fourier transformation, the frequency, normal frequency, integral minus infinite to infinite x of f e power plus j 2 pi f into t df. That only I used here. What is the range? Minus b to b, because minus infinite to infinite, the pass band is only in between of minus b to b. So we take that here, the range is a minus b to b. X of f. What is the x of f? Nothing but h of f. We are writing it is in the h of t. H of f value is e power minus j 2 pi f into t naught. And according to the definition, that is e power j 2 pi f into t df. Now I can simplify. Okay. Integral, see again, it is a changes is a minus infinite to infinite, is a b only, my students, minus b to the b. E power, both the bases are the same. You can add the powers. E power j 2 pi f. In the two functions, j 2 pi f is a constant. Here the plus value, the t minus t naught into df. I can apply the integral of exponential function, the positive exponential. The coefficient of the j value, e power the value t, that's not the t, with respect to we are applying the frequency. So the coefficient of f is a j 2 pi into t minus t naught. 1 by j 2 pi into t minus t naught. The exponential value e power j 2 pi f into t minus t naught, with the b is upper value and the minus b is a lower coefficients. Now I can substitute the upper limit in the frequency f, e power j 2 pi f b into t minus t naught minus e power, frequency is a minus here, so minus e power j b into t minus t naught. Okay, my dear students. Now I can simplify here the 2j, you can write it in the inside, e power j 2 pi b into t minus t naught minus e power minus j 2 pi into b t minus t naught whole divided by the 2j. Already we have the 2j here. So I wrote the 1 by pi into t minus t naught. What is the equation? This is in the form of Euler's rule, sine function. Sine x e power jx minus e power minus jx by 2j. So 1 by pi into t minus t naught sine function. Sine, what is the for x value here? 2 pi b into t minus t naught. So 1 by pi t minus t naught sine 2 pi into p t minus t naught. Okay, my dear students. Now I am converting these functions as a sinc function. Sinc function. Sinc means sinc theta. Sinc theta is equal to sine pi theta by pi theta. This is a formula we have. Now the equation is in the sine function. So sine pi, the multiplication factor is 2b t minus t naught. So you have to divide that function 2b t minus t naught. Already the pi is there. Already pi t minus t naught. So you can multiply and divide with the 2b only. Okay, my dear students. Multiply and divide with the 2b. Understood? So pi t minus t naught is already there. Pi t minus t naught is there. 2b term. So sine pi theta by the pi theta is, you can write it as a sinc theta. So sine pi theta, what is the theta? 2b t minus t naught. So sinc 2b t minus t naught into the 2b. Okay. The above equation gives the impulse response of the low pass filter. Impulse response of the low pass filter. So we already know the sinc function means it is passes at the t naught value, the magnitude will get, see that t naught is equal to sinc function, it is a maximum. So slowly it is decreases, passes through the origin, and slowly it is increases and passes through the origin, and so on. It is a repeated. Gradually it is a decreasing of the amplitude. So if the next value is also, it is like this. Gradually decreasing the amplitude, and here also the gradually decreasing the amplitude. In the sinc function. Understood, my dear students? The sinc characteristics, the impulse response h of t the above equation of the low pass filter is h of t is equal to 2b sine, or not the sine, my dear students, 2b sinc 2b t minus t naught. The t naught is equal to 0, means that t is equal to t naught, not the t naught is equal to 0. T is equal to t naught, sinc 2b we got. So the magnitude value is a 2b. Why? The sine by sine, according to the L'Hospital rule, can apply the derivative of sine function and the derivative of the denominator. So you can substitute that the sine is converted to the cos. So you get the 2b all. Understood, my dear students? These are low pass filter characteristics in the distortionless transmission. Okay. Distortionless transmission, ideal low pass filter characteristics. Coming to the next one, the above figure shows that the impulse response exists for the negative values of the t, but actually the unit impulse is applied at t is equal to 0 always. Thus, the response appears before the unit impulse is applied. So practically, it is impossible to implement such a system, and h of t is equal to 0 for t is less than the 0 for causal system. Okay, so practically the low pass filter, when I am taking the low pass filter, it is impossible to implement. Why? See here, the characteristics, the negative values also, it shows the response. The above figure shows the impulse response exists for negative values of the t, but actually the unit impulse is applied at t is equal to 0 always. Thus, the response appears before the unit impulse is applied. Practically, it is impossible to implement such a system, and h of t is equal to 0 for t less than 0 for causal system. We already discussed about what is a causal. Causal system depends upon the present inputs and the past inputs. It is not at all depends upon the future inputs. Future inputs means we will get at t is equal to minus values, and t is equal to 0 to infinite, only we get it is the present and the past inputs. Therefore, it is clear that although the ideal low pass filter is very desirable, but it cannot be physically realizable. With this, the conclusion, what we are saying here, therefore, it is clear that although ideal low pass filter is very desirable, but it cannot be physically realizable. So practically, the unit impulse to the filter is applied at t is equal to 0. That is, delta t is equal to 1. Impulse, unit impulse minus 1. So unit impulse at delta of t is equal to 1 at the t is equal to 0. Okay, then the impulse response. What is the impulse response for the impulse signal h of t? The impulse response of a filter should start at the most of t is greater than or equal to 0 only, and not at t is less than the 0. That is the negative values of the t. Okay, my dear students. So the low pass filter means you have to take only from the 0 to the infinite. Understood? So it is not physically realizable, ideal low pass filter. Physically realizable, because of it is before appears actually when the unit impulse is applied at the t is equal to 0 always. This response appears before the unit impulse is applied. Understood, my students? And coming to the remaining filters, we have already said that there is a 4 types of filters: low pass filter, high pass filter, and the band pass filter and band reject filter. Band pass filter and the band reject filter. Band pass and the band reject and the low pass and high pass is a vice versa. High pass filter. What is a high pass filter? Whichever it is a pass band in the low pass filter, high pass filter is a stop band. Okay. See the characteristics shown for the low pass filter. Pass band is here the pass band. This one is a pass band and is a stop band. Towards that and towards this one. But here, this is a stop band, and here whatever there is a stop band there, it is a pass band. Sorry, it is a pass band, and here also pass band. High pass filter. It allows only the high frequency values. High frequency value. The magnitude response of the high pass filter allows high frequencies in the range of 0 omega to the omega naught to the higher frequencies. Okay, and it also minus omega to the lower frequencies. Okay, in the previous we studied the realizability of low pass filter, but its response begins before input is applied. Disadvantages, my dear students. Its response begins before input is applied. This means ideal low pass filter is anticipatory. Hence, it is not physically realizable. Similarly, other filters like the high pass filter and the ideal band pass filters have frequency responses as shown here. These filters have sharp transition at cutoff frequencies. These sharp transition in the frequency response results in non-causal impulse response. That is, it begins before input is applied. Again, this means all the ideal filters are physically not realizable since their impulse response is non-causal. Impulse response is a non-causal, means it is depends upon the feature inputs also. All the filters are not physically realizable because of it begins before the input is applied. Before the input is applied, my dear students. Okay, other ideal low pass filters such as high pass and the band pass. And what is a band pass here? Band pass means it is here for the low pass filter, the stop band is from the omega naught, let us take it is a minus omega naught. Omega naught to the infinity is a stop band. Minus omega naught to minus infinity is a stop band. And coming to the high pass filter, minus omega naught to minus infinity is a pass band. Omega naught to the infinity is a pass band. But band pass filter, the same, but it does not allow in between of minus omega to omega. This is a low pass, lower cutoff frequency. Upper cutoff frequency is it allows only in between of omega 1 to omega 2. Omega 1 to omega 2, my dear students. But here it allows omega not to be infinite. The range is pass band. And it allows here the minus omega naught to omega naught. But band pass filter means it allows only the band pass, the relation is set in between of omega to the omega. It rejects all the frequencies from minus omega 1 to omega naught. What is a band reject filter means exactly the opposite here. It allows only in between of minus omega 1 to omega 1. It does not allow is a stop band. It does not allow the high frequencies. Okay, so wherever it is rejected in the not allows in the band pass filter, it rejects here. This is a stop band here, and this one is a pass band. These are all the ideal characteristics only, my students. Whenever if you go for the practical characteristics, low pass filter practical characteristics monotonically decreases. High pass filter is monotonically increases, and band pass filter is increases, and it is slowly decreases. This is a band pass filter. Allows only in between the frequencies. Band pass filter. Okay. Then it is a band reject filter. The similar fashion we have like this. This one is a pass band and the rejects. If it is a pass band means here it is a rejected. It is a rejected value, which means it is a pass band. It's opposite to the value. Here allows only the low frequency, the pass band, the low pass filter. And high pass filter, it allows only the high frequencies. Suppose it is a band reject filter. Band reject filter. It allows only the in between of omega 1 and omega 2, the upper cutoff frequency and the lower cutoff frequency. frequency, which is not allows in the band reject, band pass filter. So actually, this is a characteristics is a band reject filter, my students. Band pass filter is looks like this one. This is a band pass. It does not allows the in between the -1 omega 1 to omega 2. Okay. What we are concluding that in the distortionless transmission, whenever you are using the filters, high pass, low pass, and band pass filters, the impulse response exists for the negative values of the T. Okay, and it is an anticipatory, that is an ideal low pass filter, hence it is not physically realizable. Since the impulse response is a non-causal response. Non-causal means it is also depends upon the future inputs. Okay, my dear students. These are a very important theory part here. And in this, we can also learn that what is a bandwidth. In the band pass filter, bandwidth is the range of, the bandwidth is nothing but it is a range of two frequencies, omega 1 to the omega 2, upper cutoff frequency to the lower cutoff frequency. Okay. And signal bandwidth. What is a signal bandwidth? It is a range of significant signal frequencies which are present in the signal. It is a range of significant signal frequencies which are present in the signal. It's called the system, not the system, signal bandwidth. System bandwidth means is in between of the intervals, the frequencies of the magnitude, omega 1 to the omega 2 upper cutoff frequencies, and the lower cutoff frequency, the difference one. Okay, my dear students. Now coming to the next topic, in the analysis of the linear system. In the analysis of the linear system, so we already learned that is a system. What is a system is nothing but what are the different types of systems. It's nothing but continuous time system and the discrete time system. Again, the continuous time system is divided with the 6 characters properties: static and dynamic systems, linear and non-linear, time invariant and time variant. Okay, linear and not the linear and non-linear, stable system, causal and non-causal system, and invertibility. So actually, it is an invertibility. So already we have here invertibility also. Okay. We already discussed about this, static and the dynamic, linear and non-linear. Okay. Some examples you can see that in the last one after the completion of the concepts. So whatever now we discuss about the filter characteristics of the linear system, ideal low pass filter, okay, and other ideal filters such as high pass and band pass, we are already discussed about this one. Now the distortionless transmission also we already discussed. So see here what I told now itself, the amplitude distortion. This distortion occurs when magnitude of h of omega is not constant over the frequency band of interest, and the frequency components present in the input signal are transmitted with a different gain and attenuation. Okay, the amplitude distortion. Amplitude means if there is any distortion occurs, that distortion is amplitude distortion to phase distortions. Phase is related to the frequency. Amplitude is related to the y-axis, and phase is related to the x-axis. The frequency and amplitude. The distortion occurs when the phase of h of omega is not linearly charging with the time, and different frequency components in the input are subjected to different time delays during the transmission. The transmission here, the different gain and attenuation, and here the different time delays during the transmission. All we are getting, either it is amplitude distortion or the phase distortion when it is a transmitting volume. Signal bandwidth. See the signal bandwidth, the bandwidth of the frequency that contains most of the signal energy is called the bandwidth of the signal, denoted by F. It is a range of the significant signal frequencies which are present in the signal. Observe the waveform x of t has significant frequencies from omega 1 to the omega 2. This is a cutoff frequency. The maximum frequency is a 1. You can take always the cutoff frequency is a minus 3 dB. So 0.01. Okay. At wherever it is a minus 3 dB cutoff frequency, you can take the frequency omega 1 with the lower frequency, lower cutoff frequency, and omega 2 at the higher cutoff. The difference between these two, so that our bandwidth of the signal is omega 2 minus omega 1. All the physically obtained signals have limited bandwidth. Nothing but the signal bandwidth we have. System bandwidth. The bandwidth of a system is defined as the range of frequencies over which the magnitude of h of j omega or omega remains within the 1 by root 2 times of its midband. See the value here is a midband only. Slowly it increases, and with particular frequencies it's a constant, and again it is a slowly decreases. Both are the same here. But the cutoff frequency is seen that 0.01 for the signal bandwidth, and here the cutoff frequencies are drops 1 by root 2. So root 2 means 1.14, and 1 by root 2 means 0.707. 0.707. It drops to the 0.707, or it remains with the 1 by root 2 times of the midband. Midband means wherever it is a constant. Omega 1 to the omega. For distortionless transmission, the system must have infinite bandwidth, but physical systems are limited to the finite bandwidth. So, a system with finite bandwidth can provide a distortionless transmission for a band-limited signal if the magnitude of h of omega remains constant over bandwidth of the signal. The range of frequencies for which the magnitude h of zero system remains within the 1 by root 2 times of the maximum value is nothing but system bandwidth. The range of frequencies is a definition, my friends. The range of the frequencies for which the magnitude h of omega of the system remains within the 1 by root 2 of the maximum value. Okay, my dear students. And the signal bandwidth means it is a range of significant signal frequencies which are present in the signal. Okay. Is the difference of the signal bandwidth and the system bandwidth. Here, the cutoff frequency is a 0.01, and here the cutoff frequency is a 0.707. 1 by root 2 is nothing but 707. Coming to the next one, causal systems. Causal system. Causal system means it depends upon the present inputs and the past inputs. The system is said to be causal if h of t is equal to 0 here. H of t is equal to 0 if t is less than the 0, and h of t minus t naught is equal to 0 for t is less than the t naught. Means if the h of t is a 0, that is a causal system equation. The condition simply saying that. If input is a 0 for t is less than the t naught, when the output is also 0 for t less than the t naught. Any system which does not obey the above rules is called nothing but the non-causal system. I will explain why we are saying it is a non-causal and the causal system for h of t is equal to 0, whether it is a condition is satisfied or not. Let us see. We have the formula is there. That formula for the convolution, the y of t is equal to y of n is equal to sum of k equal to minus infinite to infinite h of k, x of n minus k. The convolution formula, my dear students. Now I'm expanding these k values from minus infinite to the infinite and so on. I take the k is equal to minus 1. So h of minus 1. Okay. X of n, k is a minus 1 means minus of minus 1 is a plus 1. Plus, and k is equal to 0. This is k is equal to minus 1 value. If k is equal to 0, in the expansion, k is equal to 0, h of 0, x of n. Plus, when the k is equal to 1, h of 1, x of n minus 1. So on. If it is the next value, what is the next value here? H of 2, x of n minus 2, so on. Plus, if suppose here you can take the k is equal to minus 2 also. It is a k is equal to 1, 2. What is a k is equal to minus 2? H of minus 2 into h of n minus of minus 2 means n plus 1 plus 2. Okay, my dear students, and so on. See here, what is the causal system is? It depends upon the present inputs x of n and also past inputs x of n minus 1, minus 2, minus 3 and so on. Nothing but is a causal. Okay. If it depends on the x of n plus 1, plus 2, plus 3, means it is a non-causal. Non-causal. Okay. In this equation, see here the x of n plus 1, x of n plus 2. These are the future inputs. X of n is a present, x of n minus 1 is a past, x of n minus 2 is a past only. So from this up to this only, Jando, I am taking the other one. Up to these equations is a causal. So it is depends upon the present input here and is a past inputs. X of n plus 1, x of n plus 2. This is an input term. So input not at all equal to the 0. When you can take these only, the h of minus 1, h of minus 2, h of minus 3 and so on. All these values is a 0, then only it is a causal system. So for that, we are taking the condition is h of t is equal to 0. Means h of t or the h of n. The discrete value h of n is equal to 0 for n is less than 1. What is a less than 1? Minus 1, minus 2, minus 2. So h of minus 1 is equal to 0. So h of minus 2 is equal to 0, this value, and so on. So if this condition is satisfied, then that signal is a causal signal, or not a signal, but a causal system. Okay, causal system. Understood? The system is said to be causal if h of t is equal to 0, if t less than the 0. As a continuous, in the discrete means h of n is equal to 0 if n is less than the 0. Okay, my dear students. Any system which does not obey the above rule is called non-causal system. If two input to a causal system are equal up to the some time t naught, then corresponding output must be equal to that of the time instant also. Okay, my dear students. So in this we can take the polyvinar criterion. A polyvinar criterion. So what is a polyvinar criterion? And here you have to derive the expression for the bandwidth also. Bandwidth function. See, polyvinar criterion. What is a polyvinar criterion? This gives the condition for the causality. This gives the condition for causality in frequency domain. Or in other words, the frequency domain is equivalent of the causal system h of omega. Consider a system with a transfer function h of omega. H of omega is nothing but the transfer function or the system function. The necessary and sufficient condition for H of omega to be transfer function of causal is integral minus infinite to infinite. The magnitude of H of j omega by the 1 plus d omega is less than infinite. Provided H of j omega is a squared magnitude, or the integral minus infinite to infinite, the squared magnitude of H of omega is less than infinite. This is the polynomial criterion. You can take this as an equation. The squared magnitude of H of omega into d omega must be the less than the infinite. Okay, my dear students. This is a polynomial criteria. If condition 2 is not satisfied, then the condition 1 is neither necessary nor sufficient. So what is a polynomial criteria? And simply you can say this gives the condition for the causality in the frequency domain. In other words, the frequency domain is equivalent of causal system. The equation is integral minus infinite to infinite, the squared magnitude of H of omega d omega is less than infinity. Understood, my dear students? And the physical realizability. The system is said to be physically realizable if it obeys the causal condition. What is the causal condition here? The H of t is equal to 0 for t less than the 0. Whether it is a physically realizable or not, but it obeys the causality condition or the causal system condition. H of omega, let us example, if I am taking the H of omega is equal to 1 by 1 plus j omega. What is the inverse Fourier transformation here? It is in the form of 1 by a plus j omega. So e power minus t mu of t is equal to 0 for t less than. So for the above system, for the transfer function is realizable in frequency domain, integral minus infinite to infinite, ln of H of j omega. The magnitude divided by 1 plus omega square d omega is less than infinity. Okay. And coming to here, the frequency domain statements can be interpreted as H of omega is a physically realizable. System may be 0 for the some discrete frequency, but it can be never be 0 for finite bandwidth of the frequencies. And H of omega for a realizable system cannot be decayed faster than the function of the exponential order. The system with the transfer function e power minus omega is realizable, whereas e power minus omega square is not as delay as for decay fast. Okay, Madam. So this is a theory part only. Now we can take that as a relation between of the rise time and the bandwidth. Relation between of the rise time and the bandwidth. If you can take, see the unit step function is passes through the low pass filter. Unit step function is passes through the low pass filter, and the output here is the ramp function. We can see the transfer function of ideal low pass filter is H of omega is having the magnitude e power j theta omega, and the theta omega is a phase and the magnitude is a j h of omega. So I am taking that as a h of omega as a g of omega and e power minus j omega t naught as a rectangular pulse with a magnitude of k in between of minus b to b as a low pass filter. That is nothing but here the minus omega less than or equal to omega and less than or equal to omega m, where omega m is a 2 pi into b. Why it is a 2 pi into b I taken? It's actually omega means 2 pi f. The frequency here I am assuming the b and the minus b1. And theta omega is a minus 2 pi f into t naught, 2 pi f into t naught, that is equal to minus omega into t naught. 2 pi f is nothing but omega. The Fourier transformation of the mu of t by using the duality property, okay, or not by using the duality property, the signum function. The signum function we already know the signum of t is equal to 2 into mu of t minus 1. If we can take the signum function, signum of t is equal to 2 into mu of t minus 1. Now I am taking the signum of t minus plus 1 is equal to 2 into mu of t. And signum of by 2 and the by 2 is mu of t. Apply the Fourier transformation, mu of omega is equal to for 1 by 2. So one Fourier transformation is we already know the 2 pi into delta of omega according to the duality property. So 1 by 2 the Fourier transformation is pi into delta of omega. Okay, my dear students, for this, so pi into delta of omega. And the signum function proper Fourier transformation, signum of t is equal to 2 by j omega. Fourier transformation. The Fourier transformation of signum of t is equal to 2 by j omega. And the signum of t by 2, what is the Fourier transformation? 1 by j omega. So use here, these are two parts as 1 by j omega. So Fourier transformation of mu of omega is pi into delta of omega plus 1 by j omega. Understood, my dear students? The Fourier transform of the response r of omega, input and the h of omega is related as the unit step function and the h of omega, and the Fourier transformation, the convolution, we will get the ramp function. So r of omega is equal to, I am taking here it is a x of omega or the mu of omega into h of omega. How we got it is a product, my dear students. Actually, internally it is h of omega, and here the mu of omega. To get the response is r of omega. What is r of omega? The t actually, my dear students. T, r of t, h of t, and mu of t, because we are giving the signal mu of t signal, unit impulse. So r of t is equal to, the convolution is between mu of t with the h of t. Now I can apply the Fourier transformation on both sides. R of omega is equal to, the time domain is convolution, means the frequency domain is multiplication, mu of omega. Okay, my dear student. Below the mu of omega is a pi delta omega into 1 by j omega, and h of omega is now multiplied. That is the response is r of omega is equal to, as per this block diagram. So r of omega is equal to pi into delta of omega plus 1 by j omega into h of omega. Now we can h of omega multiplied pi into delta of omega is a delta matrix, not the s. Pi into delta of omega h of omega plus 1 by j omega into h of omega. Is a relation between of rise time and the bandwidth. It is also very important, my dear students. Then after, delta omega exists only at omega is equal to 0, because it's an impulse function, my dear students, in the frequency. Delta of t is equal to 1 for t is equal to 0. Now the delta of omega is 1 for omega is equal to 0. Okay, my dear students. Then, and the h of omega at omega is equal to 0, the value is 1. There is a relation between of delta omega and h of omega. Delta omega is the input signal, h of omega is the output response. It's the same function we will get. So r of omega is equal to pi into delta omega plus 1 by j omega into h of omega. Whenever it is a delta omega is multiplied with the h of omega, the value is 1 only. H of omega is equal to 1. So by taking the inverse Fourier transformation of the equation, once again you can see, my dear students, in the previously the equation is here, pi into delta omega h of omega into 1 by j omega into h of omega. I keep this as a h of omega is equal to 1 because it is a multiplied with a delta omega in the frequency domain. Okay, my dear students. Delta omega exists only at omega is equal to 0, and at omega is equal to 0, the h of omega value is 1. Okay, so for that condition, the r of omega becomes pi into delta omega plus 1 by j omega into h of omega. We can apply the inverse Fourier transformation. R of omega is r of t, and inverse Fourier transformation of pi into delta omega plus 1 by j omega into h of omega. So inverse Fourier transformation of the two functions, pi into delta omega plus 1 by j omega into the h of omega. We already derived the equation g of omega into e power minus j omega into t naught. See here, h of omega is equal to g of omega into e power minus j omega naught omega into t naught. Now I can substitute this value by in the h of omega, as h of omega is replaced with the g of omega into e power minus j into omega into t naught. Okay, so inverse Fourier transformation of pi into delta omega, already we know the 1 by 2. So 1 Fourier transformation is 2 pi into delta omega, and 1 by 2 the Fourier transformation is pi into delta omega, and delta pi into delta omega inverse Fourier transformation is 1 by 2. So I replace here the 1 by 2. And inverse Fourier transformation of 1 by j omega e power minus omega into t naught. So now we can substitute directly in the formula 1 by 2 pi integral minus infinite to infinite 1 by j omega e power minus j omega naught t as a total function, and it is multiplied with positive power e power j omega into t d omega. Okay. And in the low pass filter, it is varies only in between of minus omega m to the omega m. In that, the g omega is a magnitude. Okay, the magnitude is a 1. So 1 by 2 pi. Now from minus infinite to infinite becomes of minus omega m to the omega m, and g omega is a 1 by j omega into the basis of the same. You can add the powers here. E power j omega you can take as a common t minus t naught into d1. Okay, a simple simplification only here. Now apply the integral. It becomes of e power j omega t minus t naught. Here they wrote directly that as e power jx as a cos x plus j sin x. Cos x plus j sin x. Okay, my dear students. Or otherwise, directly you can apply the integral e power j omega t minus t naught. It becomes of e power j omega t minus t naught whole divided by omega into t not the omega j into t minus t naught because omega we are applying with respect. So let us see here. If I take the integral of this function, it becomes of e power so e power j omega into t minus t naught whole divided by, because we are applying the integral with respect to the omega coefficient is j into t minus t with upper limit is omega m, lower limit is a minus omega. Substitute this one. Already we have the j omega is also there. When I am substituting the omega as omega m, e power j omega m into t minus t naught minus e power, now it becomes of minus value, minus j omega m into t minus t naught whole divided by, here the term is there, j into t minus t naught. Okay, and it is multiplied with the j omega also. This totally is multiplied with 1 by j omega or 1 by 2 pi into j omega. 2 pi into j omega. So take this 2 here. I am removing the 2. You can write only the pi because, and the t minus t naught you can write here. Okay, my dear students. So now it becomes of e power jx minus e power minus jx by 2j. sine value, sine omega m t minus t naught whole divided by, all of the 2j we got, the remaining function is t minus t naught and the pi also, pi into j omega into t minus t naught. Following matter, students. In similar fashion, we got here also, see 1 by 2 as a function with the 1 by 2 plus 1 by pi into sine of omega minus omega into t minus t naught omega m and the 0. Understood, matter, students? We'll get the integral value directly, or otherwise we can take the e power j as the cos function. The cos is a 0 values and the even values. So integral of any odd function, the 2 into this function, integral of even function only you get the even function from the 0 to omega. Here the 0 to omega m is a value is a 0. The odd function is a 0 and even function is a 2 into the even function. That becomes of 1 by 2 plus 1 by pi into sine omega m t minus the t naught by substituting the omega m as the upper limit. Okay, my dear students. And now the rise time is given as the tr is equal to 2 pi by omega m. 2 pi by omega m. What is omega m? Here the 1 by b. The cutoff frequency is omega m minus b to the b as nothing but minus omega m to the omega m. Minus b here it is a minus b or the plus b, it is omega m. The 2 pi by omega m as a rise time, the tr is equal to 2 pi by omega m. That omega m as the 2 pi by the beta, not the beta, b, sorry. tr is equal to rise time, tr is equal to 2 pi by the b. Is the cutoff frequency of the low pass filter. How we got this one? We can apply the derivative, the dr of t by dt at the t is equal to t naught in this function. The derivative of constant is a 0. And for this derivative is 1 by pi into sine function is a cos function, cos omega m into t minus the t naught. Okay, t minus into t naught. Now at omega is equal to, at omega, the 1 by tr is equal to omega m by the pi, and the tr is equal to omega m by the pi. When the tr is equal to omega m by pi, tr is a pi by omega m actually, pi by omega m. Understood, my friends? Now the relation is the tr is equal to 2 pi by the beta as and it having the characteristics also. The triple students, they know in the control system they are getting the function rise time, peak time, delay time. Delay time is it by 50%. Peak time is it's 100% to reach the time taken to reach the 50% is a delay time. The rise time is rise time and the peak time and the settling time also. Like that, the characteristics look like the 50% it reaches delay time TD, and it is a maximum peak TP. Okay, and in between there is a maximum overshoot also MP, and here there is a settling time TS, and rise time is here we'll get the rise time TR is equal. It's a 50%, 100% it is, and maximum peak TP. 100% means the minus cutoff frequency is there here, minus the TR. There's the characteristics of the rise time and the bandwidth. The bandwidth is a B, and the rise time is a TR. The TR is equal to 1 by B, the inversely proportional to each other. So inversely proportional to the each other. See, this is the characteristics. So delay time is a 50%, rise time is a 100%, TR is equal to, the peak time is also there. Okay, my dear students, and here the settling time goes like this. Understood? As omega c is infinite, the y of t is equal to 0, and omega c is equal to minus infinite, the omega t y of t is equal to r of t is equal to 0. It is also somewhat important, the Pliny-Vina criteria and the relation between of the bandwidth and the rise time. Understood, my dear students? So with this, the completion of the 4th unit here, the theory part, and in the tomorrow class we can see the problems, some more examples in the analysis of a linear system. Okay, these are different types of examples. In the tomorrow class and the day after tomorrow class, you can see all the examples. Okay, mostly in the today's class we have only the theory part only. What is the signal bandwidth and what is the system bandwidth? Okay, amplitude distortion, the phase distortion, and causality system. What is the Pliny criterion? It is the integral minus infinity for the square magnitude of h of j omega into j omega is less than the infinite. And either it is a physically realizable or not. When it is a physically realizable, when e power minus omega is realizable, whereas e power minus omega square is not, as it is decay so fast. And the relation between of rise time and the bandwidth. What is the relation here? The TR and the bandwidth is inversely proportional to each other. Why? It is a bandwidth is nothing but the frequency only matters. We already know the frequency and the time is inversely proportional. The TR is equal to what is a P? Is a frequency. The T is nothing but the time. The time and the frequencies both are inversely relations. Inversely related. Understood, by the students? Okay. In the tomorrow class, we see that the remaining topics, not the topics, the remaining examples on what we discussed, that topics we discussed with the linear analysis of the linear system, my dear students. Okay, analysis of the linear system. Understood? Okay, any doubt is there? Okay, thank you.